This is the 2160, lecture 22, support vector machines. Okay, let's do it again. So this is 2160, lecture 22, support vector machines and kernel methods. I'm Harry Asada. So this is the just a quick outline of the final 4 lectures and scheduled till the end of this class. We discussed the deep learning, the CNN, and recurrent network last time. And then that will be covered in PS number 6, which is the last one they just posted today. And today's topic is support vector machines and kernel methods. And going to next week, Gaussian processes and a Koopman operator theory for exact linearization of nonlinear dynamical systems. And we conclude this course with the final lecture on dual-faceted linearization with application to model predictive controls. So as I said, the PS number 6 is just released and having 4 programs and each covering a 4 lecture, each lecture. And then program 2 today is actually for support vector machines, the kernel method. Program 3, Gaussian processes, and program 4, Koopman operators. And you want to discuss the first 3 programs at this week's final study group meetings. And program 4 is to cover Koopman. So PS number 6, the due date is pushed to Wednesday. That's actually final lecture. So that's the schedule. And the COP number 4 is due today. Okay. So what we'd like to do today is to look at the little different story than the previous case, so focusing on the regression. So suppose actually you are, working on the self-driving cars. And key part is actually vision system, image processing, and you have to recognize the humans versus the cars. And then actually the way that your car is to react to these obstacles are different depending on what you're looking at. Actually, if the cars, it takes a certain behaviors, but if you find the pedestrians, it has to take a totally different mode of navigation policy. So first thing is to classify, what it is, right? So if that's a pedestrian, they go through, different procedures, say, where the person is going, what is the walking speed and such. That's basically a, regulation program, and they take different actions. If that's actually something else like a cars, then you take a different approach, and still you need a regression to estimate where the car is going. And then depending on that, you take different actions. So first thing you need to classify what is the situations, and that's classification problem is a very important task that we have to consider. So what we do is we capture some of the features from the image or any other sensor signals. And then in this case, it's just a 2 feature points, 2 feature variables are taken, x1, x2. and plot the data you have taken, and one class is classified to a human, the other points are classified to something else. And then you need to draw the line to classify class 1 versus class 2, and then typically we draw a straight line over here, and if the value here is actually higher than this straight line, and then you classify it to class 1. So higher than C and lower than C, it's actually the way to classify this. Now you can draw the lines in many ways. You can just put it this way and then that way, but what we like to do is to classify, separate these two sets as much as we can, as far as possible. So we actually consider a kind of a band, and then we like to classify this, one beyond this band, the other is above this band. And if this band, this actually distance of separation, we like to make this width as wide as possible. We call that the margin, right? So the question is how you find the in this case, three parameters, W1, W2, and B, so that you get the highest, the widest separation between the two classes. By the way, at the end of the day, what you find is just a few key data points like shown here are basically separating these two. And these points are called support vectors to support these actually in bands and then actually determine the widest separation between two classes. So a quick outline today. I have to say that this first half of the talk is basically undergraduate materials, and then if you have taken some machine learning class, it's being covered, I guess. And also I have some kind of overlap with the subject I teach. That's a 212 or 2120 robotics. That is to cover just the introductory part of support vector machines. So for 2160, we go deeper into this. In particular, we look at the kernel tricks and positive definite symmetric kernels. And that's actually the main part, and going to reproducing a kernel here vector space, and then your basis to functions. So let's start with the simple part. So suppose we have actually n-dimensional vector space and the feature space, and associated with these n feature variables, we have weights W1 to Wn, and actually bias term B. And what we'd like to do is to find W1, Wn, B's so that the separation between these two classes is actually broadest. Okay. Of course, we have to classify all the sample points correctly. So, if you plug in the sample, the data points in here and evaluate this linear function, if that's actually positive, then it's classified to class 1, and then the negative or 0 classified as class 2. Now, in doing this, what we need to do is basically we look at the only sign, and we don't care the magnitude. So we can pick our favorite magnitude of this function value, f, and so we do this, in the following way. So correct classifications. If actually that's higher than this, it is actually, answer is y equal plus 1, and suppose this one is class 1 or class 2. And if negative or 0, then y equal minus 1. This is the correct answer, and it's showing this on class 1 or class 2. We look at the only two class classification problem. And interestingly, these two cases can be combined and then represented by just one expression as shown here. The idea is that we multiply this correct answer y to this function, which is called the discriminant function. And say in this case, and plug in the ith data point yi, and then that would transpose xi plus b. And if whichever the case in here, this is always actually no less than 1. Because in this case, this part is actually positive. And then let me just go back to this. And we have two boundary points in x1, x2, or support vectors, x1 and x2. So as I said, scale is not an issue. So let's define fx2, which is actually on this side of the boundary, to take the value of +1. And this side is -1. We determine the scale in this way at these boundary points. Now, if that's the case, combining these two conditions together, multiplied yi, which is take either +1 or -1, times this guy, and then we scale this point to be here, the boundary to +1, the higher the point is larger than 1. So +1 times something greater than 1, it makes this one to be greater than 1 or equal to 1. On the other hand, if this is a negative value, that's why it's take the negative value, but lower than this, it should be lower than -1. So product between the two should be greater than 1 or equal to 1. And then we request all the sample points, I equal 1 to capital N, satisfying these conditions. Okay, now let's look at just the geometry quickly. So suppose these 2 points, x1, x2, are actually support vectors on the boundaries, lower side and the higher side. Now the width in here can be expressed by taking the difference x2 minus x1, the vector from x1 to x2, and the projections onto this direction, which is indicated here by a unit normal vector to this line. So if you take the inner product between the two, x2 minus x1 times the n, that inner product is to indicate this width, right? Now, since these 2 points are on the borderlines, so and as we defined x1, we make a fx1 to be -1, and for x2 that makes this discriminator function to be +1, right? And that's the way we define the scale. Okay, now let's subtract the first equation from the second one. Then what you get is 1 minus 1 equal 2 equal W transpose x2 minus x1. Now let's divide the magnitude of this vector, weight vector W, divided this equation on both sides with actually absolute value of W. Then what you get is 2 over W equal W transpose divided by its magnitude, and then x2 minus x1. But this one is actually what we did was to create the unit vector. So this is this unit vector, which is actually perpendicular to each the lines over here, right? So what this means is basically the width of these two boundary, right? So width can be represented as actually 2 over absolute value of W. Okay, now what we need to do is to maximize this width, 2 over W, which is equivalent to say to maximize 2 over W square. So this one can be represented as the inner product, W transpose and W. Well, maximizing this is to minimize this reciprocal. So, W transpose W, this is actually norm of this. If you basically minimize this, you can basically maximize this width. And best to separate these two classes. Okay, so our problem can be formulated, just one of two is just for the convenience of expression. Just to minimize 1 over half, 1 over 2, W transpose W. And the W must satisfy this condition, which is to classify all the sample points correctly, I equal 1 to n. Okay, now, well, actually, this particular condition subject to this inequality condition is a little bit difficult to deal with. So here's actually, interesting technique to apply. We create the following penalty function, okay, to eliminate any discriminant function that is unable to correctly classify or some sample points. Let's consider the following penalty function. So this one consists of the product of some parameter alpha I, and then 1 minus discriminant function. So let's take a look at the situations. And then what we'd like to do is to maximize this by selecting the proper value of alpha. Now, let's consider the 3 cases. One is that if you plug in the xi, yi, that's actually the sample points, data points on this borderlines, like x1, x2 in this case, that is to make this value to be discriminant function to be plus minus 1, and then if that is exactly on this line, that's actually plus 1. So this guy is to be 0. So 0 times alpha I, we'd like to maximize this, but I know we can't do anything. It's all 0. So for any values alpha I, if this is the case, this one is to return just a 0, right? On the other hand, if the sample point which is correctly classified, make this guy greater than 1. If that's the case, this term becomes negative, right? Negative. Therefore, to maximize this, alpha should be 0. So alpha I should be 0 for those points of which are classified correctly. Now, this is the case, the points which are not classified correctly. This function is to take the value less than 1, make this one a positive. If this is positive, to maximize all this, alpha should take a large value. And then let's take some kind of bound in M. So the maximum allowable value M is to be taken for this actually samples. So what this means is that if the choice of W and V cannot actually classify all the points correctly, you get the sum terms that to be in this category. So make this one to be positive. So alpha can take a large value. So you have a large, penalty values, M times this one, right? So that's a way to avoid, to eliminate, rule out those W and V, which are unable to classify all the points correctly. So just as a summary, the above penalty function becomes 0 if all sample points are correctly classified. No penalty, 0. And it takes a large value only when some samples points are incorrectly classified. So what we do is actually we append this guy to the main term which we would like to minimize. This is the minimize. Then we actually add this second term, which is the penalty function. And then if something wrong, this penalty function is so large that actually such pair of W and V cannot actually make the minimum case. So please note that any discriminant function that cannot correctly classify some samples, even one sample point, is eliminated in the minimization of the above function. So what we like to do is to minimize this function. And what we do is we just take the following technique. We like to minimize this, okay, with respect to W, B, and alpha 1 to alpha n, okay? Now, so this other whole is to be minimized in here. Now, first, we can actually swap this max and this minimum in this way. So here, what you do here is basically, when you take this minimization, we minimize this for an arbitrary value of alpha I. Alpha I has never, within this actually, inner part, minimization of this, alpha is not actually, determined. That's actually, outer, maximization. If you swap a maximum and minimum in this way. So when you take this minimization, you have to do this for an arbitrary value of alpha i's. Okay, so suppose that you can actually do that. You can find the minimum values of w and then the b, which may be the functions of alpha, and then outer loop you maximize that inner part, which has been already minimized with respect to w and the b. You can actually further maximize that with respect to the alpha. Okay. The key point is that you have to take this minimization for an arbitrary alpha. For an arbitrary, no matter what alpha you take in here, this solutions should be valid. Okay, so let's do that in here. So this is to minimize. So the necessary condition for that is basically its derivatives with respect to w and with respect to b must be 0, right? So from this condition, differentiating this with respect to w, you can just, from here, you can get the w. And from here, w is involved only here. So the coefficient for this is alpha minus yi and xi. That comes out. So just putting it on the right-hand side, w equal summation alpha I, yi, xi comes out from this condition. And from this condition, the second one with respect to b, you picks up alpha I and then minus and yr, and the summation must be 0. We get the second equation. Therefore, let's substitute this one back to this. Okay, the w, at least after taking this minimization, w is actually to take this form, which is function of alpha, right? So put in this one here and here and here, you get this expression, okay? Now, because of this condition, if you multiply alpha to yi and b, you get actually 0. B is a constant. You can factor out. So that term becomes 0. So we can get rid of it. The rest of the part is this big summation to the double summation part and this double summation part are basically the same. This is 1/2 and this is 1. So the remaining part is minus the 1/2 of this term, right? So this is something we like to minimize with respect, maximize with respect to alpha, okay? That is to minimize the overall L, okay? Now, so we minimize this subject to this constraint, okay, constraint. Now, this one is a little bit complicated. It's, however, this is just a quadratic form, with respect to alpha. Alpha is shows up in here and here, right? Xi, yi are basically constants, actually given the sample data. So we like to maximize this with respect to alpha subject to this one. Well, because alpha subject also to this conditions must be between 0 and m. So you can't actually solve this analytically, but you can use any kind of quadratic programming technique that can actually solve this one quite effectively. So there are a bunch of effective techniques available, so we rely on those techniques to solve this problem. So given the sample points, we can find the w, which is to maximize the width. So originally we have to deal with this equations, but plug in this optimum w into this, we get the discriminator function written in this form. Now, we did not mention much about the B, but a B can be represented, it can be solved quite easily. So, if you pick any of the support vectors, which rely on the marginally hyperplanes or boundary, right? For any support vector, it is to satisfy this. Actually, this one is to take a +1 or -1, and depending on which side of the boundary you are looking at. So solving this, you can basically find the B, which is given by this. I now replace W by this guy, and they end up with this one. So once you find the alphas from this quadratic programming, you can actually determine all W's and the B's in this way. So that is support vector machines. Now here's actually a challenge we have to look at. So if these two sets of sample points are separable with a straight line, or in the high dimensional case and hyperplanes, that's easy. That's a linearly separable problem. But we did see this kind of situations. No matter how you draw these straight lines, you can't actually separate these two with the hyperplanes. So there's no margin at all, right? So that's actually the problem we faced some time ago. Remember that the exclusive OR problem is basically the counterexample to the simple perceptron, the neural nets. And then, this is very simple, truth table, but input-output relationship cannot be tuned with the linear discriminator functions or, a simple neural net. So, yeah, let's look at this problem again. So at this time, we use this discriminator function, W1 x1, W2 x2 plus B. And you remember that these two points are classified to class 1, and class 0 cannot be separated, no matter how you draw this straight line. So what we introduced a third variable, x3 equal x1 times x2. And we dealt with this nonlinear discriminator function, x1 plus x2 minus 2 times x1 x2 minus 1/3. For instance, this set of parameter values can classify this correctly. You remember that, right? So it's not actually two-dimensional x1 and x2, but we actually introduced our third axis, and then we successfully separated the two sample points into two classes, right? So this hyperplane can, separate this. Hyperplane is basically linear expression. So what this means is that we have augmented the feature space or input space from a two-dimensional vector to a three-dimensional vector, phi of x, x1, x2, and then x1 times x2, right? So this is the way we did. Okay, so the algorithm support vector machine that can be extended to the transformed feature space. So let's expand this one in this way. So how can we find such a new variable in a systematic manner? That's actually being questioned, and we happen to come up with this idea. But in general, what is actually the way to separate? Otherwise, not a linearly separable problem. So here's the place we actually expand the feature space by using the so-called kernel functions. Now, we reformulate the support vector machine optimization program. You find it totally the same story as before, even though we expanded the space from the original vector, input vector space x to feature space of phi x. We get the same equation. Here's the first discriminator function. I replace the x variables by phi times phi of x, and then x replaced by phi of x over here, right? Now, this phi x is to have a little bit higher dimension, right, as we looked at before. So what we can do with this is that we can do the same thing in different discriminator functions for this one. If the sample is actually higher than this and the border is to take the plus more over higher than the +1, exactly on the border, it's take the +1, and then this side -1, so forth. So we put together, we can actually combine these two into just one conditions, right? And then this must be met for all the capital N sample points. And actually, the width is given by this, and I just replace x2 minus x1 by phi x2 minus phi x1. The same story to maximize this width, so we like to maximize this, and then minimize by taking the reciprocal. We minimize this, subject to this one, exactly the same story. So at the end, we find the optimum, alpha, and then with use of that alpha, we can actually write the W, that's weight, as a function of alpha I and the sample point yi, and then actually sample point xi transformed to phi. Then this one was originally xi, now replaced by phi xi, and I go 1 to n. Right, and we solved exactly the same type of quadratic optimization problem. We just solved this one subject to this. Only the difference is that the x is now replaced by phi of x. Now this technique is called the Kernel trick. Now using the optimal weight, this one, the optimal discriminator function, or sometimes called the support vector classifier, is given by this form, right? Phi of x, and then replacing the x by phi, and then phi is now replaced, W is now represented by this. So here's the phi, and then also W also includes phi over here. So as you put these two together, and one is actually, phi transpose, the other is phi. So you can just put these and phi vectors together to create the inner product, phi transpose phi. And then let's replace this function by, kxix, which is called the kernel function. Okay? This kernel function has several special meanings, special properties. But basically, just generalizing this result, this kernel function is basically map from x and then xi and then x vectors to some scalar quantity, because inner product is a scalar quantity, right? So this kernel function k is some actually in a vector in the space capital X. This is basically the same dimension as the phi xi, and then the other one is same x space where phi x reside. So from here to actually scalar real quantity. Okay, so that is actually defining this kernel function. Okay. It is an inner product of two feature vectors in a high dimensional space, because phi x is typically higher than dimension of x. Now this can be computed without obtaining the high dimensional feature vector. And what this means is that all you care is value of this kernel function, and this kernel function, as far as you can evaluate this kernel function as a function of x, I, and then x, that's all set. You don't need to go back to phi. So that's what it says. Okay. If you deal with only x and xi, both are lower dimensional vectors, computation may be expedited quite significantly. Okay. And the quadratic optimizations, remember that these two shows up as a kernel in a product. So again, we don't need to touch the this expanded feature vector phi, but instead we just deal with this kernel function. This is a little bit difficult to understand. So let's work out a simple example. This is a example of a kernel trick. So now let's think about the simple two-dimensional vector x1 and x2. And first example is so-called a yeah, this type of functions, okay, this type of functions. So here what you have is inner product of vector x and then x prime, okay, this is scalar quantity, plus some constant, let's say c, and then take a square of that. Let's take a square of that, okay? So, we look at the situations where kernel functions is given by this expression. Just let's imagine, okay? Interestingly, this can be, decomposed to the, we can rewrite this expression into the one that is actually inner product of new feature vector function, phi of x and phi of x prime. Let's see how it works. So inside of this we have this is the inner product of the two-dimensional vector. So this one x1 and x1 prime plus x2 times x2 prime, right? So that's inside of this. So let's expand that one. Okay, expand that one. So first term x1, x1 prime, expanded this way, x1 square, x prime 1 square, and actually second term x2 square, x2 prime square, and then actually c square comes out this way, and then cross term 2 times x1, x1 prime, x2, x2 prime, and the other terms, right? Interestingly, this expression can be written in this way, okay? Can be written in this way. So let's actually, compute this, inner product. This times this is x1 square, and then x1 prime square, and I'd pick the second, component here, x2 square, and then x2 prime square, that's sitting here. And the third component, square root of x1, x2 times square root of x1 prime, x2 prime. If you multiply these two, it becomes 2 times x1, x1 prime, x2, x2 prime. In this way, as you continue this, you can just confirm that the product between this vector and this vector, exactly provided this lengthy expression. So if you define this one to be your new phi vector, and then this one to be phi x prime vector, we now successfully express this kernel function originally coming from here as an inner product of expanded vector phi x. Okay, please actually do this on your own. Now, so the point is that we started with this, but we expanded to 6-dimensional vectors. But if you take the inner product of these two, it's nothing but just the result is this guy, because we did it back way. But if you just multiply these two, you get to this. And this one is the kernel function we originally introduced. So this one can be expressed to in a product of expanded, augmented variables, feature vectors, phis. So kernel trick is something like this. So we can also go back to support vector machines, and we can actually evaluate this just simply. We end up with this guy, right? This discriminator functions. X is replaced by phi, and then optimizing W, and then plugging in that one, we end up with this, and where we see phi x is to shown up only as an inner product. So we replace this one here, and then in fact we consider this kernel function, in which we have just in the computations much simpler than this, because x is 2-dimensional vectors, remember? And then actually, just to take the inner product of 2-dimensional vector, the plus this constant, and the square of that result, you basically compute this one, in a much simpler way than dealing with the 6-dimensional vectors in here. So please note that the function can be evaluated directly by using the lower dimensional input vectors, actually 2-dimensional x, without actually transforming the data to the higher dimensional, this feature space, 6-dimensional space. And this is called the kernel trick. Okay. Now, I just showed you one lucky case. How general is this? Yeah, this one's good, but is it really possible? That's actually, we need to discuss. But at least you can just find that they significantly, reduce this kernel trick can significantly reduce the computational load, right? And then more importantly, we basically, reduce the not linearly separable program to a linearly separable program by recasting the input space to high dimensional feature space, right? So that's actually a very good and plus. So there are many different type of kernel functions depending on the application areas. So in supervised learning, this kind of quantifying this, the kernel functions is very useful and being used quite widely. And in general, any type of supervised learning, some quantifying the similarity between the two data points, how close they are, is critically important, right? So kernel function quantifies this similarity or nearness of data, encoding some features in its functional structure. So there are numerous functions. The first one, the dot product kernels, or sometimes it's called polynomial kernels, like the one we discussed just now. And then another type of kernel function, it turns out to be very much widely used, is radio basis functions. This one is called differently. Some say the squared exponential kernel or Gaussian kernels, 3 names at least. That's all given by this form, right? X minus x prime, the norms of that, the norm square divided by 2 times some parameters L square. And we did use this in the function approximation using the radio basis function, right? And also sigmoid kernels, given by this type of tangent hyperbolic, which is showed -1 to +1. This kind of function sometimes used. Okay, so kernel trick is kind of amazing, interesting. But how are these kernel functions related to high-dimensional feature space? Basically, this one, connected by expanding this, so we successfully found the phi x and phi x prime, right? And then in a product between the two, it's basically the same one as this. Do we see the similar phi x prime for this radio basis functions? How about this? But there are many other kernel functions. Can they all have the that's a special expression phi x and phi x prime, and then actually in a product between these two phi x and phi x prime gives you this kernel function? Are we just lucky in picking up that one, or are there any general properties that allow us to do this? That's actually the theoretical question that we'd like to look at. So one important property is called the positive definite symmetric kernels. Okay, so that kind of kernel trick is possible when kernel functions satisfy certain properties. And most important property is positive definiteness. Now let's look at that. So how we define the positive definiteness of a function? We have never done this, so we introduced the following technique. So that's actually, we need to define the kernel matrix. Okay, given the set of vectors x1, x2, xm, and M is whatever you want, okay, or any sample vectors you pick, okay. Then we evaluate the kernel functions for these sample points, and then put them in matrix form. If we have m points, you get the m by m matrix. This particular matrix is a very special matrix, but it's a type of a gram matrix, right? So we take all combinations of x1 through xm. First one, x1 and x1, and then this guy. And then second one here is x1 and x2. And then along this line, x1 and xm. And then second line, x2 and x1, blah, blah, blah. At the end, you have xm, xm. Okay, so you can create m by m matrix. Okay, so this is called the kernel matrix, created from kernel function, and that any arbitrary set of sample points. Okay, now the second definition, which is very important, is definitions of positive definite symmetric kernel. Okay, kernel is a function, but I know we define the positive definiteness by using this kernel matrix. Our kernel over and set x and x and x to r is basically a scalar quantity. That's actually a kernel function. It's said to be positive definite and symmetric if for an arbitrary samples, okay, from x, the associated kernel matrix is positive semi-definite and symmetric. So, symmetricity is obvious, right? So as you change this, it should be actually the same. That's actually, you can check the original kernel function quite easily. But the positive definiteness is defined to be the positive definiteness, in fact, the positive semi-definiteness of the kernel function. Okay? So please just pay attention to this little difference. Okay, associated kernel matrix must be positive semi-definite and symmetric. Then the original kernel function is called positive definite. It's a little bit complicated, but that's actually the way it is actually discussed. Okay, so how you check whether this matrix is positive definite? Actually, you can multiply m-dimensional vector from both sides, sandwiching this m by m matrix with the row vector c, and then column vector c, and for an arbitrary c vector, this must be this quadratic form, which is actually scalar quantity. Must not be negative. That's actually the definition of this matrix K to be positive semi-definite. Cool. Okay, now under these conditions, if the kernel that you are looking at, kernel function is positive definite and symmetric, then we can guarantee that the feature map expanded the function phi x always exists. So this is actually one of the very important theorem on supporting underpinning this field. It's also called reproducing a kernel Hilbert space. Okay, now let's actually K to be positive, definite, and symmetric kernel. Okay, and it's actually mapped from x times x to the scalar quantity, real quantity R. Okay, then there exists a Hilbert space H and the mapping phi x to H, such that this kernel function kx x prime equal inner product of this map phi x and then phi x prime. For an arbitrary x, you pick from capital X and then x prime. Okay, now some of you are a little bit scared by this word, the Hilbert space H. Well, despite actually a very rigorous definition to mathematical treatment needed in some actually areas, but in a 2160, we mean by Hilbert space is nothing but an infinite dimensional vector space where inner product is defined. Inner product must exist in this space. And this is some mathematical actually point. Any kind of a Cauchy sequence converges within its actually its own Hilbert space. It's called a completeness. And this allows us to do all kind of a mathematical treatment. Unless this condition is actually satisfied, it's not impossible. So we basically bound the class of space that must satisfy these two conditions as the main conditions. Okay. So why I use this one H here? Because sometimes, which I show you some example, when you expand the original input space, X space to phi, augmented space, the augmented space sometimes becomes infinite dimensions. That happens, for specific cases, which I explained. So instead of just confining ourselves to X to some dimensional high space, but we can extend it to infinite space. So of course, this mapping does include the case that the X mapped to some finite dimensional space, which is actually a special case of a Hilbert space. So we include that. Okay. So we function fx can be treated as an infinite dimensional vector. Phi x or fx or whatever the situation we're dealing with, actually this phi is actually putting this one to infinite space. Okay, so we'll discuss this moment more. Okay, now I gave up to prove this existence theory. That's a little bit involved, so regrettably I gave up on that one. It takes a long time, but along with this, improving this, we got this kind of byproduct, which is very interesting. It's called for positive definite symmetric kernel, the associated Hilbert space has a following a very special property. It's called reproducing property. So if you take the inner product between the kernels and any functions you put in there, it is to produce the original function H. It's called the reproducing property. Yeah, of course, when you take the inner product actually between these two functions, I did not use the just a regular transpose times the original vector, but instead we use this particular sign, which may be a little bit broader. In fact, if this guy is actually infinite dimensional vector or the function, you have to take the summation. Excuse me, summation must be replaced by the integral. So we prefer that this actually representations, which is a little bit broader. Okay, so whatever the case, this Hilbert space is very special, and a positive definite symmetric kernel has this wonderful properties. So if you check the positive definiteness by creating the kernel matrix, if that actually tends to be positive semi-definite all the time, that is actually a valid kernel function, and for that there exists this actually phi function. So let me just take a quick example. So this is actually the case of radial basis functions. As I said, radial basis function is actually one of the kernel function. And obviously this particular one has actually a symmetric properties, right? Even though you swap these two, you get the same thing. So that's actually symmetricity is no problem. Okay, so the challenge is that this particular form, can we really expand it to the feature vector phi x and the phi x prime? How come we can actually split this one into two? Here, the x and the x prime are mixed over here, right? We like to split this one clearly between x side and the x prime side. Let's see how it works. So first, let's actually expand this. So inside of here, we have actually, x transpose x, and then that comes in here, and the x prime transpose x prime comes in here. So at least 2 terms comes out. But we have, as you expanded this, we have cross term x transpose times x prime, right? Now this is exponential, so we can divide into these 3 products, right? Exponential of this guy, and then exponential of this guy, and actually cross term is sitting here. Now these 2 terms are okay, as stated here, it is separated between x and then x prime. That's fine. But the last one is cross term, a mixture. Can we really split this one between the 2, which are to be taken as inner product? So let's apply the Taylor series expansion for this cross term exponential in here. Right. So remember that this is actually a scalar quantity. As you take the inner product, it becomes a scalar quantity. So you can expand it this way, right? So first one, x transpose x prime, and the next one 1/2 exclamation mark, and then x transpose x prime's square, and then add to the 4th, and then actually expand it this way. This is nothing but the serial, Taylor series expansion. Now, it's a little difficult to see, if the vector x is actually the vector quantities. So let's look at the simple case where x is basically scalar x. Okay. Even though we extend it to a vector, it's the same thing, but I know notations are horribly complicated. So let's check it with the scalar case x. So what you do is the following. So this is one group, right? This is another group. And then with this, let's think about this expansion taken from here. And for this part, oops, I'm sorry. X prime is actually taken this way, the other group. Okay, so first we define this, and then actually its prime version is actually, putting here, right? So let's actually take the inner product between these 2, right? So inner product this times this, plus this times this, plus this times this, right? So first one is 1, agrees with this. And then second term, if you multiply this and this, it is to provide this, right? Third term, square root of 2, square root of 2 to 2, and then add it to the 4th, and then x to, basically, x, we're dealing with the scalar case, x square, x prime square, that actually agrees with this, right? So likewise, this one gives this guy. So at least this particular term, we can split between all x terms and x prime terms, right? And then multiplied by this to this, multiply this one to this. Yeah, we can split the this radial basis function kernels into this infinite dimensional space. So this is my phi x. This is my phi x prime. Of course, as I said, if actually x is the full vectors, yeah, this notation is much more complicated, but it's possible. You can check it, right? But I know that's possible. We can write it this way. So this is an interesting point, yeah, and also you can check this guy is to be a positive definite. You can form the Kernel Matrix, and you can prove the positive definite semi-definiteness. And so this is to be positive definite symmetric kernel function, which has this phi expression. Okay. Now, this radio basis function, sometimes called the Gaussian kernel or squared exponential kernels, is one of the most widely used kernel functions in machine learning, in particular support vector machines and the Gaussian processes, which we discussed this Wednesday. Okay, it has only one parameter, L, in here. It's called the characteristic length scale because L is small. You have a very sharp functions, and then large actually it covers a broader range. So yeah, it is tuned by selecting the right value of L. So this is your design parameters you deal with. Okay. So when you use this, kernel functions in some ways, it is to measure the distance or similarity between two data points, x and x prime, right? So in this case, it's just the distance between the two is to give this guy, right? And actually, when you measure the distance, we do that with the characteristic length, length scale L. For support vector machine kernel functions, back to this, we can put this one so in this. So even though when you use this radio basis functions, the phi function is infinite dimensions, so it is impossible to compute. But don't worry, as far as you just keep it in this form, it's so simple. And this kernel functions is involved in this quadratic optimization program too. So you never ever worry about phi. So just a reflection and a summary for today's lecture. We look at the support vector machine, which maximizes the margin in two class classifications, and then mathematical derivation of the optimal classifier with the largest margin has been obtained. Right, and we look at the linear separability by revisiting the exclusive OR problem, and then we introduce the kernels and the kernel trick and the positive definite, the symmetric kernels, and the reproducing kernel Hilbert space, and then again the radio basis functions is very useful, and we look into this. And interestingly, as you expand it to Hilbert space, it is basically infinite dimensional feature vectors. So it is to provide lots of information by expanding it, recasting the original input x1 or whatever x vector to the high dimensional space, and many problems that can be reduced to linearly separable classification problem. So that's all about it. Thank you for your patience, and sorry for the internet problem today.